All right, this is for Chemistry CP, debriefing on the homework assignment titled Nuclear Decay and Half-Life Worksheet. Part A, write equations for the following nuclear decay reactions. Make sure that both mass numbers and atomic numbers are balanced on each side. Number one, decay of polonium-218 by alpha emission. All right, well, polonium-218, I'm sure I will find it soon. Here it is, atomic number 84. So PO with an atomic number of 84 and an atomic mass of 218 emits an alpha particle. An alpha particle is the nucleus of a helium atom consisting of 2 protons plus 2 neutrons, making the total atomic mass 4. What is left, the daughter has to add to the alpha particle to match the numbers for the parent. So 218 minus 4 is 214. 84 minus 2 is 82. And consulting with the periodic table, atomic number 82 is lead, Pb. So there's number one. That's just a little blip. Number two, decay of carbon-14 by beta particle emission. Well, carbon-14, carbon is atomic number 6, and beta particle emission is the emission of an electron. So off goes the beta particle, which you can consider to be an electron with 0 mass and -1 electrical charge. The daughter added to the beta particle has to match the parent. So 14 minus 0 is 14, and 6 minus -1 is 7. Consulting the periodic table, atomic number 7 corresponds to nitrogen. Or if you like, -1 plus 7 equals 6. Number 3, decay of chlorine-32 by positron emission. Chlorine is atomic number 17. Positron emission is a negatively charged electron, which you could write as the electron symbol with 0 mass and a positive electric charge, hence the name positron for it. The daughter has to combine with the positron to equal the parent. So 32 minus 0 is 32. And 17 minus 1 is 16. On the periodic table, atomic number 16 is sulfur. Number 4, decay of promethium-142 by electron capture. Promethium is atomic number 61 with atomic symbol PM. In the process of electron capture, now we're showing something that takes place before the daughter is formed. We are adding an electron, which has 0 mass and a -1 electrical charge. So after it is captured, is basically converting a proton into a neutron. The total mass doesn't change. The number of protons is reduced by 1. So 61 plus -1 equals 60. And consulting the periodic table, atomic number 60 is neodymium, Nd. Number 5, half-life. The half-life of phosphorus-30 is 2.5 minutes. If you start with 35 grams of phosphorus-30, how many grams would remain after 20 minutes? Well, the amount of mass that you end up at the end is equal to the amount of mass that you start off with times 1/2 raised to the number of half-lives. So if the half-lives were 0, of course, that means no time has gone by. 1/2 to the 0 power is 1, and you still have your starting mass. If 1 half-life has gone by, then you have half of your original material. If 2 half-lives have gone by, then you have 1/2 squared, which is 1/4 of your original material remaining. In 20 minutes, if each half-life is 2.5 minutes, then the number of half-lives that have gone by would be 20 divided by 2.5. 20 divided by 2.5, and I see I need to clear my calculator and get it working right. So 20 divided by 2.5 is 8. I guess I could have done that one in my head. The number of half-lives. And plugging that into the formula, we would say we started with 35 grams, and we're multiplying it by 0.5 raised to the 8th power. And that will give us our answer. How many grams remain? Well, 35 times 0.5 raised to the 8th power. And you can kind of make out the calculator says 0.13671875 and two sig figs, but I'll write it to 3, 0.137 grams at most. Okay, so that's rounding slightly up, and 3 sig figs instead of maybe the 2 that it deserves. Number 6. The half-life of polonium-210 is 138.4 days. How many milligrams of polonium-210 remaining after 415.2 days if you start with 2 milligrams of the isotope? Well, the formula hasn't changed. The final mass that you end up with is equal to the initial mass that you start with times 1/2 raised to the number of half-lives. In this case, we would take 415.2 days and divide that by 138.4 days to tell us how many half-lives have elapsed. 415.2 divided by 138.4 is, exactly the nice whole number 3. I'm shocked. Shocked, how can that be? Plugging it into the formula, we are starting with 2.0 milligrams. We might as well just leave it in units of milligrams, times 1/2 raised to the 3rd power. You could almost do that in your head. It's 2 divided by 8, but let's go. 2 times 1/2 raised to the 3rd power is 0.25 milligrams, because we're in the same units as the original quantity. So 2.5 milligrams. Number 7, 20.0 grams of a radioactive isotope are present at 1 p.m. and 5.0 grams remain at 2 p.m. How many half-lives have gone by? If 0 half-lives had gone by, then we would have 20 grams. If 1 half-life had gone by, we would have half of 20 grams, which is 10 grams. If 2 half-lives have gone by, we would have half of 20 grams, which is 5 grams. So N equals 2 half-lives have gone by. How long is the half-life of the isotope? Well, from 1 p.m. to 2 p.m. is a duration of 1 hour or 60 minutes. And in that duration of 1 hour or 60 minutes, 2 half-lives have elapsed. So the half-life is 30 minutes or half an hour. Part C, predict how many grams will be left at 2:30 p.m. Well, that would be one additional half-life. Starting with the 5 grams that we have at 2 p.m., one half-life later, we should have half of 5 grams. And therefore, we should end up with 2.5 grams as our answer. We don't need no stinking calculator. This concludes the debriefing on nuclear decay and half-life worksheet.